Hello guys, in this video we will talk about some of the activation functions that we'll be making use of in our neural networks. Okay, so let's get started. So I have listed here some of the most commonly used activation functions. Those are Sigmoid, ReLu, Leaky ReLu, tanh, and there are many more like max out, ELU, etc. Okay, so today in this video we will concentrate on these four things, and along with that we will also talk something about Softmax as an activation function. Okay, so we will have the in case of neural networks, we will apply some activation functions to hidden layers and output layers, right? So what are those activation functions that we are gonna learn today here? Okay, so first one in the list is sigmoid, right? So we all know the formula for sigmoid function is 1 by 1 plus e to the power minus z. So this z can be a number, right? In case of machine learning, this z will be theta transpose x. In case of neural network, it will be w into x plus b. If it's with layer 1, it will be 1. If it's with layer 2, it will be w2 x plus b2, right? So whatever it is, we will apply this formula in order to compute the sigmoid value. What this does is, this squishes the numbers outputs in the range of 0 and 1. So you will not find any values which are less than 0 and greater than 1 once you apply the sigmoid function. Okay, so that's what sigmoid does. Now coming to tanh. So tanh formula is given by e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. So what this does is, this is actually an improvement over sigmoid. You can call improved sigmoid function. So instead of squishing the data between 0 and 1, this will squish the output between minus 1 and plus 1. Okay, and additionally it centers the data around the mean 0. So this will help in a better way while converging the cost function in neural networks when compared to sigmoid. Okay, so now that we have seen sigmoid and tanh, we will see something called as ReLu. ReLu stands for rectified linear unit. Okay, and this is a simple function which is stated like this: max of 0 comma x. X here is our input. Max of 0 comma input, you can take it that way. So the output will be, if the input is negative value, output will be 0. Otherwise, the same thing will be dumped as an output. So that's what rectified linear unit is doing. Now we have something called as Leaky ReLu, which can be treated as an improvement over ReLu. Improved version of ReLu. You can think of it as this way. So what this does, instead of squishing everything that is negative to 0, it will add some value to that, so that if you plot it, there will be some slope for the values beyond 0, or for the values which are negative. Okay, so in a minute from now, I will implement all these activation functions in Python and also plot how they look like. So it will be clear what I am talking here in case of Leaky ReLu. Okay. Now coming to our last activation function, Softmax. So this outputs the value between 0 and 1 for each of the probable outputs that we have in our case. And sum of all those probabilities will be equal to 1. So the outputs for each of the probable outputs will be probabilities for each of the outputs. So how do we calculate it? The mathematical formula is e to the power x divided by sum of e to the power x. Okay. Now we will see how we can implement all these, and let's try to visualize sigmoid, tanh, ReLu and Leaky ReLu. Okay. So for that, let me spin up a Jupyter notebook. I'll bring it here and let me import exp from math library. From math, import exp, exponent function. Okay, so I have imported it now. So what I'll do, I'll say I'll create a list of inputs. Inputs is equal to, I'll use a list comprehension I for I in range of, I'll have some negative values and positive values both. So I will have a list of numbers ranging from -10 to 10. Okay, so if you, okay, so there is a spelling mistake, it should be range. Now if you check inputs, it's a list ranging from -10 to +10. +10 is exclusive, so it will not be in the list. So this is how our inputs look like. Now let's define a function. Let's implement Sigmoid. It will take input x and it will, what it will return? It will return 1 by 1 plus exp of -x, right? So this is what Sigmoid returns. So now what I will do, I will create a variable outputs is equal to, so I will create a list for this. Sigmoid of input for input in inputs, right? So it will take each number in this list and then pass it on to this Sigmoid function and it will calculate the outputs. Now if you check the outputs, wait, I think there is some mistake. Return 1 by 1 plus exp to the power exp to -x. So the values should have been between 0 and 1. So why it's not giving the desired result? So 1 by 1 plus exp of -x. Okay, put. So let's test this out. Sigmoid of -10. Okay, so this is not right. So there is something wrong with this. Okay, so I think this is where the problem lies. Okay, right. So now you see it has been fixed. The problem was with the brackets and the way the computation was carried out. Okay, so we have fixed it now. Now let's call it again and see the outputs. Now you can see the outputs are ranging between 0 and 1. None of the values are outside of that particular range. Now let's plot it. So in order to plot it, let me import a library which will help us to visualize the stuffs. So it will be import matplotlib.py plot as plt. So let me import it. And then what I'll do, I'll just call plt.plot. I will call outputs. So you see, this is how our Sigmoid function looks like when we plot it. Now let us implement tanh function, right? So let me define a function and call it as tanh. I will take the input. Okay. So now what is the formula for this? I have written it here, right? So e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. So let's implement this. So it's simple to implement. So nothing. Return. So it is exp to the power x minus exp to the power minus x divided by, okay, so let me enclose everything in bracket to avoid the errors like we faced for Sigmoid. Okay, so I'll say exp of x plus exp of minus x. So this is what we are returning. So I'll enclose everything in a bracket. Now what I'll say, I'll again say outputs is equal to tanh of input for input in inputs, right? So now if you check outputs, all the values will be between -1 and +1. In case of Sigmoid, we had the values between 0 and 1. In case of tanh, we will have the values between -1 and +1. So if we plot it, plt.plot outputs, see, now This looks like a sigmoid, but sigmoid was ranging from 0 to 1, but this tanh is ranging from -1 to +1, right? And you can see there is a sharp bump in this case here. Why I am highlighting it? Because this will help us in speeding up the learning process in case of neural networks. Okay, so that's just the extra information. You need not process that right now. Okay, so let's forget that. So this is tanh. Okay, now let us implement ReLu. All right, so let me just say ReLu. This stands for rectified linear unit. Okay, so now I'll say define ReLu. I'll take input x. My output will be max of 0 comma x. So this is what ReLu does, right? So now let me take outputs is equal to ReLu of input for input in inputs. Okay. So now let me call it as outputs just to be consistent with the naming convention. Outputs. If I check this, all the negatives will be turned to 0 and all the positives will be returned as it is. So for the positive values, you can say it as a linear function. We are just returning whatever we are supplying to it, right? So if I plot this plt.plot and say outputs, you see all the negatives are turned to 0 and all the positives are returned as it is. So from 0 onwards, you can treat ReLu as a linear output function. It does nothing to that. Okay. Now let's implement Leaky ReLu. Leaky ReLu. Let me define a function called Leaky ReLu. It will take input and it will return? It will return max of 0.1 x comma x, right? So that's it. So let me write that return max of 0.1 into x comma x. So whichever is greater, it will return that. Now I'll store outputs is equal to Leaky ReLu. So this should be a list comprehension, right? So Leaky ReLu of input for input in inputs, right? So in its syntax, okay, so it should not be here. Now if I check outputs, you see it has not turned all the negatives to 0, but there is a slope for the negative values. So let me show you why I am calling it as a slope. If I plot it, plt.plot outputs, you see instead of getting flat at 0, we have some slope for the negative numbers. So it's not reducing all the negatives to 0, but instead it is returning some values to that. And again after 0, it's just a linear, we can say it as a linear transformation, right? So 1 will be 1, 2 will be 2, 3 will be 3, 9 will be 9, so on and so forth. So this is how you implement these activation functions in Python. Now, in order to talk about Softmax, let me import NumPy. Okay, we cannot usually visualize Softmax, but we can show the probabilities that it will output, right? So let me define Softmax. Input will be x and return will be np.exp of x divided by np.sum of np.exp of x. Okay, so this is what it will return. So what is this formula? I have just written the Softmax formula in terms of Python using NumPy. Okay, so that's it. So now let me take only few inputs. Inputs is equal to I for I in range of, let's take some 5 numbers, guys. Okay, 0, 1, 2, 3, 4, something like that. So if I check my inputs, it's 0, 1, 2, 3, 4, right? So output will be softmax of inputs. So that's it. So now if I check my outputs, these are all the probabilities associated with each of these inputs, sum of which will be equal to 1. So how I can look at that sum? I'll just say sum, which is a Python inbuilt function, and I'll say outputs. So the sum will be equal to 1. So this is how you implement these simple activation functions in Python. But while working with neural networks, you do not have to implement anything. The Keras library or TensorFlow library will take care of all these implementations by itself. You just need to call those library methods and then pass in your inputs and expected outputs. So it will do the job for you. Okay. So this is it for this video. If you have any questions on this, you can reach out to me on implementation of this, or if you want me to cover any other activation functions, you can write that out in comment section. I'll cover that. Now there are some issues associated with Sigmoid, tanh, ReLu, right? I will cover those issues with the activation functions in my next video. Okay. So if you guys have not subscribed to my channel, please do subscribe. If you like the content that I am creating, please share it with your peers so that they will also understand the workings of neural networks and machine learning. So till we see in the next video, guys, happy learning. Stay tuned. Bye bye.